Hi everybody, I hope this video finds you well. In today's video, we're going to be taking a look at another example of running the two-sample proportion procedures that we discussed in the previous video. In this example, we're going to see sort of an interesting use of those two-sample proportion procedures. That's a little bit different than the sort of standard use, but it'll be the same formula, same setup, so it will give us a chance to sort of practice the exact same procedure, just in a little bit of a different setting. So let's jump right in and take a look at this example. So we're going to suppose that you are conducting a psychological study to see if people are risk adverse. And all we mean by risk adverse is that they sort of prefer to minimize the risk that they're exposed to. So to study this, what you do is you collect a random group of 250 adults. You then separate your group into two groups, one with 100 adults and one with 150 adults. The first group, you offer them an opportunity to play a game where you flip a coin, and if it comes up heads, they win $10, and if it comes up tails, they lose $10. Now, from our study of expected value and stuff, not that it's relevant in this question, but just to make sure you understand sort of how the study is working, this is obviously a fair game, right? They have an equal chance to win $10 as they do to lose $10. So it's a fair game, and it's relatively low risk because the worst thing that could happen is you only lose $10, and, there's not much to gain either. You're only going to win $10. So we're going to call this group, this first 100 adults who are offered this opportunity, the low-risk group. The second group, you offer them the opportunity to play a game where you flip a coin, but if it comes up head, they win $100. However, if it comes up tails, they lose $100. So obviously this is also a fair game, equal chance to win or lose, and the value of winning and losing is the same, but it's a much higher risk proposition. If you lose, you're losing $100, where you also have a lot more to gain. If you win, you're winning $100. So we're going to call this the high risk group, right? So in both cases, the people are being given this offer to play a fair game, but in one of the games, the first game, it's a low risk game, whereas in the second game, we're sort of classifying it as a high risk game. So we find that 43 of the low risk group and 52 of the high risk group agree to play their respective games. So what we're going to do is we're going to carry out at alpha equals 0.05 a hypothesis test to test the claim that the people are risk averse. What we mean by that, in other words, we're going to test the claim that a higher percentage of the low risk group will agree to play their game compared to the high risk group. Because if people are risk adverse, more people, a higher percentage of people should be willing to play the low risk game compared to the high risk game. So we're going to carry out that hypothesis test. And then we're going to do a little bit of error analysis. We're going to say, would falsely deciding that the percentage who are willing to play is the same between the two groups, when in reality the low risk group has a higher percentage, be a type 1 or type 2 error. So we'll run a hypothesis test and then do a little bit of error analysis here. So let's start off by identifying what type of hypothesis test this is going to be. So we can see right here in the description of the claim that we're talking about a percentage. So that tells us we're either working with the one sample proportion or the two sample proportion. Now, the reason I said this is sort of an interesting example is that keep in mind that initially we just took a group of 250 adults. But notice that we split those 250 adults into two groups, the 100 adults who got the low risk offer and the 150 adults who got the high risk offer. So even though we initially started with one sample, we sort of broke that sample into two pieces. This is going to be a two-sample proportion hypothesis test. And of course, again, the categorical variable that we're looking at here, whether or not they're willing to play their particular game, it is a binomial or Boolean categorical variable because people are either saying, yes, I'm willing to play, or no, I'm not. All right, so let's go ahead then and talk about what the hypotheses are going to look like. So the null hypothesis, whenever we're doing one of these two-sample proportion hypothesis tests, is that the percentages or the proportions are going to be equal. So we'll say that the proportion for the low-risk group, because we have information about them, is going to be equal to the proportion for the high-risk group. For the alternate hypothesis, we know that it's going to be some inequality between these. Let's go back and read our claim. We're trying to test the claim that a higher percentage of the low-risk group will agree to play their game compared to the high-risk group. So we're saying that the percentage who agree to play should be higher or greater than for the low-risk group than the high-risk group. That does mean that this is going to be a one-sided test, but of course we want to be a little bit more specific there. We would call this a right-sided test. That means that when we get to step 4 and we want to calculate the p-value, we will need to do 1 minus whatever we find on table A. All right, let's get to our conditions then. So both are random and representative. That is definitely stated. Of course, both samples are random and representative because they originally came from one big sample of 250 random adults. So that should be random and representative there. For this guy, we would say both samples less than 5% of the population size. Well, in this case, it is a little bit unique because we don't really have two separate populations. We're basically testing two different variables. So we should be able to get away with just saying lots of adults because that's sort of what we're testing here. So we'll be all good with that. And then for condition 3, this is the one about the successes and failures in each particular one. So the successes in the low-risk group, if we look back, there were 43 people from the low-risk group that said that they were willing to do this. So we had 43 successes. That is greater than or equal to 5, so we're good there. For the failures in the low-risk group, well, remember that the low-risk group, there were only 100 adults, and 43 said that they would do it. So 100 minus 43 gives us 57, and that is also greater than or equal to 5. So we're good with successes and failures for the low-risk group. Now let's look at the high-risk group. For the high-risk group, we saw that 52 people agreed to the offer. So that was 52, greater than or equal to 5. And for the failures for the high-risk group, well, if we had 52 said yes, right? And remember that there were 150 adults in the high-risk group. 150 minus 52 is going to be 98. That is also greater than or equal to 5. So we're all good. So all the conditions are met. The only sort of interesting thing here is that we don't really have two separate populations. We're really testing two separate variables. So notice we only had to mention one population in condition 2. And that is a little bit unique. All right, for step 3, we've got our test statistic here. It's going to be Z, as I always when working with proportions here. So numerator P1 hat minus P2 hat, denominator square root, P tilde, 1 minus P tilde, 1 over N1 plus 1 over N2. So that means we need to know P1 hat, we need to know N1, P2 hat, N2, and of course that P tilde. So P1 hat, that is the first sample proportion. That is the percentage in the low-risk group who agreed to the offer. So that would be the number of successes in the low-risk group, 43, divided by the sample size, which was 100, which is a very nice, easy calculation. That's going to just be 0.43. The sample size for the low-risk group was 100. Remember, low-risk has to be group 1 because we put them first in our hypotheses. For P2 hat, that'll be the number of successes, 52, which was how many people agreed in the high-risk group, out of the sample size, which was 150. So if we go ahead and do that, 52 divided by 150, let's see what we go ahead and get there. Let's see, 52 divided by 150, looks like we should get approximately 0.347. And N2 was 150. And then, of course, P tilde, this is that pooled sample proportion, so we're going to add those successes together, 43 plus 52, and add the sample sizes, 100 plus 150, which is 95 divided by 250. And if we do that, 95 divided by 250, looks like we should get 0.38. And as we mentioned in the previous video, that 0.38 is in between these two, between 0.43 and 0.347. You also notice that the 0.38 is a little bit closer to the 0.347 because, again, the second group had a larger sample size. So let's go ahead, throw all that stuff in there then. We'll just pull this guy up here. And looks like Z should be equal to 0.43 minus 0.347 divided by, and then we have our square root, 0.38, 1 minus 0.38, 1 over 100 plus 1 over 150. All right, as always, we'll go ahead and do the numerator and the denominator separately. So up top, 0.43 minus 0.347. Looks like we should get 0.083. And in the denominator, we can just type that in as long as we're careful with those parentheses there. 0.38 times parentheses 1 minus 0.38 times parentheses 1 divided by 100 plus 1 divided by 150. And looks like in the denominator, we should get 0.063. And after we do that division, 0.083 divided by 0.063, looks like we should get 1.32 as our z-score. All right, now we're ready to go ahead and get our p-value from table A. But we can always go ahead and start by drawing our bell-shaped curve. There's our null. This is a positive 1.23, so our z-score is somewhere over here, 1.32. And our p-value, well, we're doing a right-sided test, so you want to make sure that you're shading into the right there. So we're shading in all this stuff over here. That'll be our p-value. Then we can look up on table A. So again, we're looking up 1.32. So let's go ahead and look that up, 1.32. There's 1.3012. So it looks like we're using 0.9066. So 0.9066. 0.9066. That is all the stuff to the left here, 0.9066. To get that actual shaded area, that p-value, we will need to do 1 minus in this case. So 1 minus 0.9066, which should come out as 0.0934. So there's our p-value, about 9.34%. We can go ahead and make our conclusion then. For our conclusion here, our p-value compared to the alpha of 0.05. So again, the alpha is 5%. The p-value is about 9.34%. That does mean that the p-value is larger in this case. So we have a large p-value, which means that we are going to fail to reject HO. So since we failed to reject HO, that means we failed to find evidence. So we'd say no significant evidence that, well, no significant evidence for our claim, which was that the percentage for the low-risk group is higher than the percentage for the high-risk group. So no significant evidence that the percentage of people in the low-risk group who are willing to play is higher than the percentage in the high-risk group. So in other words, we actually failed to detect any evidence that people actually are risk adverse. Now, does that mean that humans are not risk adverse in general? Not necessarily, right? We had a very sort of basic way of testing this, right? We basically created these two games, one where it was winning or losing $10, one where it was winning or losing $100. We might say that maybe $100 for most adults isn't enough of actually a risk to really see any sort of results. But at least according to what our data shows, we didn't see any reason to believe that a higher percentage in the low-risk group are willing to play compared to the high-risk group. So we failed to reject HO in this case. So in some ways, this was just a chance for you guys to see another sort of step-by-step of going through the two-sample proportion procedure. The one sort of unique thing I really want to just call your guys' attention to was that in this case, we sort of manipulated the standard structure of the two-sample proportion procedure, where you normally have two separate populations. And we did this more where we were sort of taking one population, but maybe asking them two separate questions or testing them under two separate conditions. And that can also be done using this sort of two-sample proportion procedure. So just a sort of alternate thing to see there. In terms of identifying the procedure, though, notice that in the language of Part A here, we still saw mentions of percentage, so we knew that we were working with proportion, and we also saw that there were two groups, the low risk and high risk. So all the same indicators were there. Let's quickly go ahead and look at Part B as well. We'll just go ahead and put this on a separate page. Let's go ahead and grab our hypotheses. So let's just grab that so we can bring that over. All right, so we'll just pop that onto this page here for Part B. Okay. There we go. Okay, so there were our hypotheses. Carried a little bit of extra stuff as well. Sorry about that. Let's just get rid of that and that. Okay, so there were our hypotheses, right? We were saying that the null was that the two percentages would be equal. The alternate that was that the low-risk group would be higher. So let's go ahead and read this error again. So we're saying we're falsely deciding that the percentage who are willing to play is the same between the two groups, when in reality the low-risk group has a higher percentage, be a type 1 or type 2. So in this case, we're saying we're falsely deciding that the percentage who are willing to play is the same. So how would we end up deciding that the percentages are the same? Well, that's if we failed to reject that HO. If we kept that HO around, then we're basically saying that the low risk group and the high risk group have the same percentage. So this would include a fail to reject HO, which the type of error that happens if you fail to reject HO, or that can potentially happen, is a type 2. So it would be a type 2 error, which is where you fail to reject HO, but HO is false. So, in other words, by failing to reject HO, we're basically keeping this guy around, which says that the percentage from the low risk equals the percentage from the high risk. But HO is false, meaning this guy was wrong, and the percentage for the low risk group was higher than the percentage for the high risk group. So that error described would be a type 2 error. In our next video, we'll be moving on into a new class of hypothesis testing called global hypothesis testing.